All right, today we're going to be talking about topic 9.2, single slit diffraction. You will notice that when we look at the IB syllabus for this section, it's a little bit shorter than 9.1, and there's only one equation here, whereas in 9.1 we had a ton of equations, a bunch of stuff with simple harmonic motion. So single slit diffraction. The essential idea, single slit diffraction occurs when a wave is incident upon a slit of approximately the same size as the wavelength. We'll usually be talking about light, so we'll talk about slits that are approximately the size of visible light wavelength, very, very small. But really, any wave will diffract when it goes through an opening that's roughly the same size as the wavelength of that wave. Let's see. Take a look here. This one's really just going to be mostly about the nature of single slit diffraction, is kind of what you need to know about, be able to describe the effect of adjusting the width of the slit on the pattern, the first interference minimum, qualitatively describing patterns produced from white light. We'll go through all that. And notice again, there's only one equation, theta equals lambda over b. You might want to review a little bit your double slit interference patterns in Young's double slit experiment that we talked about earlier on in the year. And that will kind of move into this quite nicely. So the first thing we talked about is that diffraction is most noticeable if the wavelength of the wave that's being diffracted is basically equal to or a little bit larger than the opening. If the wavelength of the wave is much smaller than the opening, you won't get much diffraction at all. So we're talking about waves that are incident through a small slit, a small opening, that is approximately the same size as the wavelength of the wave. So again, take a moment to kind of think back on the double slit interference pattern that we got while we had bright spots and dark spots on the screen, why those occurred. Remember, we're talking about path difference and constructive and destructive interference, where the path difference is either a half of a wavelength or some integral of a half wavelength or a whole wavelength. Now, the strange thing is that with just a single opening, you can get kind of a similar pattern. You get at certain angles, you will end up getting constructive or destructive interference. And the reason for this is this thing called Huygens principle. And the idea is this, that when a wave front is moving forward, when it basically all of the wave phenomena, refraction, diffraction, reflection, can all be explained if you imagine that every point on a wave can be the source of a new wave. And let me see if I can kind of explain that to you real quickly. So here I've drawn two wave fronts traveling from left to right. Let's just review our wave properties a little bit. Remember that wave fronts are meant to be the same points on a continuous wave, all connected. They could be the crest, they could be the troughs, something like that. So we just draw the wave fronts, and then we draw a ray to indicate their direction of motion. What Huygens' principle said is that every single infinitesimally small point on a wavefront can be considered the source of a new set of circular waves. And then by doing certain maths and things like that, you can look where all these waves will overlap, and what will happen is they will be creating the next wave. Now, when the wave's just traveling straight, that seems kind of straightforward, but this can explain things like refraction, and it certainly can help explain diffraction, where if we have a very small opening, remember that when a wave front hits this barrier, some of the wave will hit that opening, a lot of the wave will just bounce off the barrier and reflect back. But the part of the wave that's in that opening is going to be like a bunch of little small sources of new waves. And those will all be traveling out in all directions, and so you'll get different effects happening because of that. And that's ultimately what diffraction is about. It's kind of a rough explanation, but it's the general idea. It's known as Huygens' principle. So then this is a diagram that helps explain why you're going to get an interference pattern with a single slit. You're going to get bright and dark, just like we did with double slit, with some differences, a little bit slight differences. But notice that all of the waves here that are just traveling straight through the opening towards the screen, they're all going to have the same path difference or no path difference, and therefore you're going to get a bright spot in the middle. But since diffraction is occurring and these waves are traveling out not just straight, but they're going in all directions, right? You're going to get certain angles where some of the light rays will meet up. You can pair them up with other light rays in the middle where there's a half of a wavelength path difference, and you're going to get destructive interference. And then this one will be a half wavelength path difference from that one, this one from that one, and the ultimate result is that all of these waves will cancel each other out, and you'll get a dark spot on the screen at some angle. At an even larger angle, things will pair up more evenly rather than meeting with this wave meeting with this wave, having a full wavelength. And this one's going to have a full wavelength with that one. And so you'll get a bright spot. Notice that the angle here is 3/2 of the wavelength. And then at another angle, everything will meet up out of phase, and you will get a dark spot. So we're going to end up with through a single slit, we're going to end up with a pattern of bright, dark, similar to the double slit, but with some minor differences. And here's another diagram of it somewhat. What you'll notice is that right in the middle, so here's our single slit opening here, and right in the middle as we go across to the screen, we're going to get a central bright spot. Okay, it looks like this. This is what it actually looks like, right? This is kind of on the left here is a graph of the intensity. And then we will get a dark spot on either side of it, okay, where there's no intensity. And then we will get another bright spot that is much less intense than the central one. And then another dark spot. And then another bright spot that is also less. But this is the single slit interference pattern that occurs. A central maximum and then bright, dark, bright, dark. In the equation, when we start talking about the angle that we'll be solving for, the angle that we're talking about is from the middle of the central maximum, okay, from this point here, all the way to the first dark spot. That is the angle that we'll be solving for and using in our equation, okay, from the middle of the central maximum to the dark spot. Here's perhaps maybe a little bit more clear graph of the intensity of the light on the screen relative to the angle on the screen. So here is 0 radians. These angles are going to be in radians also. So 0 radians straight across from the opening of the slit, and you'll see that's where you get your central maximum. At some angle, you're going to get this little dark spot, and then you'll get another bright spot that is much less intense, and then a dark spot, and then less intense, and then another dark, and then less intense, and so on. Again, the angle that we'll be solving for in the equation is the angle from the center of the maximum to the first dark spot. So let's take a look at the equation. The equation in the data booklet says theta equals lambda over b. Never mind that this lambda has a little bar in it. That was the only lambda I could find for this PowerPoint. Lambda over b. Now this is kind of weird because every website and everything you look up is going to use different variables. Notice in this image they say that capital D is the width of the slit. Actually, for IB we're going to say B is the width of the slit rather than capital D. So that's how wide the opening is. And just to reemphasize that theta is the angle between the central peak, the middle of the central peak, and the first minimum. It's measured in radians because we could use trigonometry to solve for this, and it would be sine theta equals lambda over b. But since we're talking about small angles, the sine goes away. B is the width of the slit that the wave is traveling through. Okay, so it's a relatively simple equation. And one of the things that IB wants you to notice is how this equation, how it will, and how the interference pattern will be affected by a couple of things. So one is, if I change the slit width, what will happen to the interference pattern? Stop and think about that for a little bit. If I make the slit wider, what happens to this pattern? Remember that slit width is b. So if b gets larger, because this is an inverse relationship, theta will get smaller, which means my whole pattern will stay roughly the same, except everything will shrink towards the middle there. So the dark spots will get closer together, the bright spots will get closer together if I make my width wider. So that's one effect. And the opposite would be true if I made my slit narrower. The other thing to think about is, how does changing the wavelength of light affect the pattern? Since wavelength and theta are directly proportional, notice that the smaller the wavelength, the smaller the angle. So smaller wavelength light would have, actually I should draw that in blue because blue is a smaller wavelength, would have a smaller width to its central maximum, and so on, as opposed to something like red light, which would have a wider central maximum. And your textbook actually has a really good picture of this, so I've just added it to this presentation. Here's the single slit intensity pattern for white light. So if I shine white light through a single opening, notice that the central maximum is actually going to be white because all of the wavelengths meet at the same spot. So you're going to have a white central maximum, a white spot in the middle, and then you're going to see a rainbow that's going to be blue, red, yellow. That's not right. That's not right at all. It's going to actually go from blue to red. Okay, so Roy G. Biv backwards. So One of the things to look at with this picture is that it's not quite right, the colors they chose. All right. Here is an IB question dealing with single slit interference. Take a look at it, time yourself, hit pause. Please hit pause and time yourself if you want. Give yourself 90 seconds to see what the answer is. Okay, let's work through this one just a little bit. So remember that our equation is theta equals lambda over b, whereas theta is measured in radians. So the question is, what is the width of the central maximum? First thing you need to remember is that the width of the central maximum is going to be not just theta, but it's going to be 2 theta, because theta is from the middle to the edge. So we're going to have to do double that, okay? So we're going to double everything, first of all, 2 lambda over b. And then we got to remember that when we're dealing with radians, it's kind of a cool thing. But an angle in radians times the distance d will give you the opposite side there. So if I just take my angle in radians times the radius of my circle, this is not exactly a circle, it's a triangle, but you can imagine this being a huge circle. If I multiply it by the radius, then I will get this segment there. So what I need to do is take this whole thing and multiply it by the distance to the screen, and that will give me the width of the central maximum, which gives me answer A. Hopefully that's what you got. All right, here's one more to try. We just talked about this a few slides earlier, so hopefully this one's easy peasy for you. But hit pause, think about it for a little bit, and see what you get for your answer. Okay, so again, we look at our equation. Theta equals lambda over b. Remembering that, so the wavelength will affect the width of the maximum. Smaller wavelength will give us a smaller width maximum. So the smallest wavelength light should be the first color you see, and then it should increase outward. So we have to remember that blue is the smallest wavelength, red is the longest wavelength, and that leads us to C as being the correct answer. And finally, here's a math problem that comes from an old IB exam dealing with single slit diffraction. It's worth 2 points. Hit pause, look at the numbers, pull out your calculator, see what you can do. All right, let's see if we can go through this one real quickly. Remember our equation, theta equals lambda over b. So we'll just plug in numbers for lambda and for b and get theta. The first thing that you're going to have to remember here, we've got 620 for the wavelength, but remember it's 620 nanometers. So looking at your data booklet, you'll know that's times 10 to the negative 9th meters. Great. And then we just need to divide that by the slit width, which will give us 0.45 times 10 to the negative 3rd, since that's in millimeters. When doing that math, that gives us the angle to be 0.0013777777. And again, if I want to know the distance between the center and the first minimum, then I need, this is the angle. Now I need to find the distance, and I just do that by taking my angle multiplied by how far away the screen is. So multiply that answer by 3.4 meters, and I will end up with an answer of 0.00468, which is roughly 4.68 millimeters. When I check for sig figs, I will round that to 4.7 millimeters. There you go. Easy peasy. Okay, let's just review whether or not we covered everything we were supposed to, the nature of single slit diffraction in general, describing the effect of slit width on the pattern. We talked about that. Determining the positions of the first minimum, that's from the equation, and qualitatively describing single slit diffraction patterns produced from white light. Great, we've covered all that. We've worked with the equation. Make sure to read through the guidance suggestions. That's always helpful as well.